once we have all the steps, now let us see that how to convert one form to another form. So, for that we will take a famous example of Cp minus Cv. So, we know that Cp minus Cv is equal to R for ideal gas. So, what will be the value for any realistic system? It is not R in general, it is only R in case of an ideal gas. So, in order to understand that, we will go to the general formula of Cp and Cv. So, you know Cp is T del S by del T at a constant P, and Cv is T del S by del T at a constant V. So, we can start with any of that and see whether the other one is coming up or not. So, we will start with Cv. So, Cv is T del S by del T at a constant V. Now, since we have that, we can immediately write the Jacobian form as Sv and Tv. We have explained that. So, whenever this V comes, we can usually do that, because it is that form where you remember u V by del x y, if V and y are same, then we can write as del u by del x at a constant y. So, we are just from here we are writing this one. Now, once we have that, we need to bring P t, remember, because we also need to bring P for the reason that there is a Cp term which involves, as you can see that Cp term involves a P. So, we need to bring P t. So, we got P t here, and then we have to multiply with P t, and we have T v already here. Okay, in order to make so this is fine. You can also multiply with T p instead of P t if that makes life easier. So, I will do that with T p instead of P t for a reason T p, and here also I have to do the same thing T p, less number of calculation, nothing else. So, now I have these 3 terms here 1, 2 and 3. So, let us call that equation 1 and I will do it separately. So, first term is just T, we do not have to do anything. Let us do this one. So, del T p by del T v is nothing but del P by del V at a constant T. Now, by definition you know, whenever you see that, it is nothing but inverse of del V by del P at a constant T, the inverse of that. Now, what is del V by del P at a constant T? It is, you are using pressure at a constant temperature, and therefore, the volume will reduce. So, del V by del P. So, you know from the definition that isothermal compressibility kappa T is minus 1 by V del V by del P at a constant temperature. So, therefore, this quantity is minus V kappa T is del V by del P at a constant temperature. So, I can write that as minus V kappa T and inverse of that, which means it is nothing but minus 1 by V kappa T. So, you keep it as equation 2, and then we start with the middle term. This term we are going to start with S v and T p. So, del S v and del T p, they are nothing in common. So, we have to write in a matrix form as this. So, del S by del T at a constant P, then del S by del P at a constant T, then del V by del T at a constant P, and del V by del P at a constant T. So, this is the matrix that we got, and you have to evaluate each of the matrix. Now, we see that we got the Cp term here, del S by del T at a constant P is nothing but Cp by T, and we got isothermal coefficient of thermal expansion here, as you know that alpha is 1 by V del V by del T at a constant P, which means this quantity is nothing but alpha V, this quantity. Now, on the right hand side I have del S by del P at a constant T, and that is not immediately understandable, but we can use the Maxwell relation here S p T v, and you know that del S by del P at a constant T, which is coming down, is del V by del T at a constant V, which is going up. So, therefore, we can write del S by del P at a constant T is nothing but minus of del V by del T at a constant P, minus of. Now, what is del V by del T at a constant P? Again we are talking about isothermal expansion which is 1 by V del V by del T. You look at here, minus of this quantity is minus alpha V. If you compare with this quantity, you can see that it is nothing but minus alpha V. So, you can write minus alpha V here, and del V by del P, which is again isothermal compressibility. As you know that isothermal compressibility is kappa T, which is minus 1 by V del V by del P at a constant T. So, this quantity is minus kappa T into V. Now, I have all the 4 quantities. Now, let us multiply that and see what we get. We get Cp by T minus kappa T V, minus minus becomes plus alpha square V square. Now, let us call that equation 3. So, from all the equations what we get is Cv equal to T multiplied by this quantity Cp by T, or you can just straight away write minus Cp by T kappa T into V plus alpha square V square multiplied by, go to equation 2, minus 1 by V kappa T, minus 1 by V kappa T. Now, what we say, we just multiply with T first. So, we see it is minus Cp kappa T V plus alpha square V square into T, and then into will not jump the steps. So, now we will multiply with V kappa T, we get minus minus plus Cp kappa T V by V kappa T minus alpha square V square T by V kappa T. Now, V kappa T cancels giving us Cp minus V and V square cancels giving me V. So, minus alpha square V T by kappa T. So, now therefore, Cp minus Cv is alpha square V T by kappa T, and that is what the answer is. You see, it is almost straightforward. I just took from one and went to the other, and it was very smooth that way. So, the thing is that you can do many such things, and one thing you can prove is that this quantity is equal to R for ideal gas. You can try that yourself. Now, we can do one more, which is shown in the Mathematica. Let us go back. So, let us do this one. Let us do delta G by the crazy one, delta H at a constant V. Let us see this one. So, shall we get that particular answer or not? Let us try. So, delta G by delta H at a constant V is how much? Let us see. First itself we can write delta G V by delta H V. Okay. And then we write delta G V by delta T P, delta T P by delta H V. Now, once we have that, we need to know certain quantities of G. So, del G equal to V d P minus S d T. So, therefore, it is advantageous for us if we have T and P quantity. So, this is particularly fine, and for H it is V d P plus T d S, I guess. So, remember our SPTV thing, SPTV, and H is a function of S and P. So, these are the variables that we get. Also, you can remember that H is nothing but U plus PV, and therefore, DH is DU plus PDV plus VDP, and DU plus PDV, DU is DQ plus DW. So, TDS minus PDV. So, TDS plus VDP. So, that is perfectly all right. So, these are the things that we will need. So, these are the things that we will need in order to calculate that. So, this is a product of these two quantities. So, now let us separate them and write that. So, del G V by del T P is equal to del G by del T at a constant P and del G by del P at a constant T, del V by del T at a constant P, del V by del P at a constant T. So, this is let us say equation number 1, and then we are taking only the first term of the equation number 1. Now, del G by del T at a constant P, let me see if I wrote it correctly. Now, del G by del T at a constant P is how much? You can get that from here. Del G by del T at a constant P is minus S. So, this is nothing but minus S, and then del G by del P at a constant T is nothing but V, and del V by del T at a constant P we know again it is isothermal coefficient of thermal expansion alpha V, and this quantity del V by del P it is minus kappa T into V. We got all the 4 for the first term, and this is going to give us kappa T S V minus alpha V square. Now, right hand side del T P by del H V, del T P by del H V is of course inverse of that quantity. So, we are going to do this one H V, or first of all we are going to write the inverse itself as T P, because we are taking inverse because we want H to be in the numerator. Now, for H what are the variables that are important? As I said, dH is VdP plus TdS. So, both S and P are important, but let us see with T itself we can get something or not. So, we can write that del H by del T at a constant P, del H by del P at a constant T, del V by del T at a constant P, del V by del P at a constant T. We need to get del H by del T and del H by del P. So, we can get that easily from this equation. For example, from this equation itself we can get that. Let us take a derivative with respect to T at a constant P. Once we do that, this quantity becomes first term becomes 0, because it is at a constant P. So, the second one gives us del S by del T at a constant P, and T del S by del T at a constant P is nothing but C P. So, the first term is C P. Now, let us take a derivative with respect to P. So, del H by del P at a constant T is, the first term is giving us V del P by del P at a constant T, which will be 1 which will be V only, plus T del S by del P at a constant T. So, now V plus T and del S by del P at a constant T, we have to use Maxwell relation. We are going to do that. So, now again we are going to remind you that it is S P T V. So, del S by del P at a constant T is minus of del V by del T at a constant P. We have used the Maxwell relation here. So, what is the del V by del T at a constant P? You know, it is coefficient of thermal expansion again. So, therefore, it is V minus T, and then del V by del T is coefficient of thermal expansion, but alpha into V. So, it will be T alpha V. So, C P V minus T alpha V. Now, what is del V by del T? Again, coefficient of thermal expansion multiplied by volume, and that is minus kappa T into V. So, we got all that. So, we got minus kappa T V C P minus alpha V into V minus T alpha V, which is minus kappa T V C P minus alpha V square plus T alpha square v square. Let us see if I am okay. T alpha square v square, yeah. So, we got two quantities, this was our 1 and this is the second one. So, let us say I write as 2 and this one I write as 3. So, now our original equation was the 1, from 1 we get that in order to do this particular derivative, which is del g by del h at a constant v, del g by del h at a constant v was product of two quantities, del g v by del T p multiplied by del T p by del g v by h v, and this we wrote as del g v by del T p multiplied by del h v by del T p inverse. Now, we got this quantity as this one. So, and now we write from equation 2 and 3 del g v by del T p, we got kappa T S v minus alpha v square let me see, and then this inverse quantity I have to divide by the whole thing minus kappa T v C p minus alpha v square plus T alpha square v square, because the quantity that we got we have to take the inverse of that, and that is the inverse that we got. So, which means, so now see in order to match the result which is here, we have C v here. So, let us convert C p to C v just to match the result, otherwise it is fine, just to see whether it is coming there or not. So, we know that C p minus C v is T v alpha square by kappa T. So, therefore, C p is C v plus T v alpha square by kappa T. So, from 3 we can write that, no, not from 3, we can just write from 2 itself, from 3, this equation 3, this will be 4 then. So, from 3 we can write minus kappa T v C p minus alpha v square plus T alpha square v square equal to minus kappa T v C v plus T v alpha square by kappa T minus alpha v square plus T alpha square v square. When you multiply that, we get minus kappa T v C v minus kappa T cancels, we get T v square alpha square minus alpha v square plus T alpha square v square. Let me see, minus kappa T v C v, kappa T cancels, minus T v square alpha square. So, now these two terms cancel, giving us minus kappa T v C v minus alpha v square. So, therefore, the result is little bit simpler, is that kappa T S v minus alpha v square. So, therefore, del g by del h at a constant v is kappa T S v minus alpha v square divided by minus kappa T v C v minus alpha v square. At least one v can go, and kappa T s minus alpha v divided by minus kappa T C p minus alpha v. Now, if I see the expression in Mathematica, it says, okay, I take minus on both sides. So, I get alpha v minus kappa T into s by kappa T C p plus alpha v, or alpha v plus kappa T to C p, just for the sake of symmetry, alpha v plus Oh, this is CV, no, this is CV, not CP. Okay, and let us see the mathematical result now. So, they say alpha V minus beta into S, and there beta is our kappa T, remember, then alpha V plus beta into CV, kappa T in CV. Yeah, so this matches with that of Mathematica. You see that starting with any derivative, we can actually convert it to the one which can be measurable. For example, alpha is coefficient of thermal expansion, volume can be measured, and then of course, if entropy cannot be measured, we can again express entropy in terms of other quantities. Or entropy is also can be measured, as you know that from the derivative of free energy with respect to temperature. So, therefore, all of these things are measurable, and we can actually get that what if enthalpy is changed and the free energy, what will be the change in the free energy if enthalpy is changed at a constant volume. So, that is really interesting and intriguing that we can do that with the standard techniques that are there. These things will be very difficult to do. So, some of the derivatives will take more time with Jacobian, but thing is that since it is logical and you can go directly step by step without remembering anything, you should be able to finish it within the time. That is what so, but you need more practice, and we are going to do some practice problem after this of changing thermodynamic derivatives from one to another, along with some other problems related to the free energy itself. Okay.